Now that we discussed the correspondence between polar coordinates and points in the plane, we are ready to talk about converting polar coordinates to and from Cartesian coordinates. So in the following example, let us convert a point given by its polar coordinates to Cartesian coordinates. So to do this, let us again draw the picture of the polar coordinates. And figure out where the point with these polar coordinates lives in the Cartesian plane. So this is the Cartesian plane. These are the axes of Cartesian coordinates. Let us put the axis of polar coordinates to coincide with the x-axis. So this here is the polar axis as well as the x-axis in the Cartesian coordinates. So we know that to find the point with coordinates 2 pi over 3, we want to draw the rotation of this polar axis counterclockwise by the angle pi over 3. So this would be the rotation. And so we must then measure 2 units corresponding to r in the positive direction of the rotation of the polar axis we have here. So let's say after we measure distance 2 in the positive direction, we end up at this point here. So this is the point with polar coordinates 2 pi over 3. To convert it to Cartesian coordinates, let us draw a right triangle, like so. So we will project our the point that we just found onto the x and y axes, like so. And so the question is, how do we determine this length, which is equal to the x-coordinate of our point, and this length, which is equal to the y-coordinate of our point? So of course, in the right triangle here, we have angle theta, and we know that this here is a right angle. So it gives us that since we know the length of the hypotenuse is equal to r, right? By construction, we said we have to go distance r, and so this must be r. So we know 2 things in this right triangle. We know this angle and the length of the hypotenuse. Our goal is to find length of these 2 sides, because this side, of course, is also equal to y. So from the picture, we have that x is equal to r times cosine theta, because x here is the side adjacent to the angle theta. So we have to multiply hypotenuse by cosine of the angle here. Similarly, y is equal to r times sine theta from this right triangle. And so this formula will be used from now on to convert polar coordinates to Cartesian coordinates. So it applies for all values of r and theta. In particular, for our point here, we will have x equals r times cosine of pi over 3, so that's r times 1/2 equals 1. Y is equal to r times sine of theta, which is pi over 3, and that is equal to 2 times root 3 over 2 equals root 3. And so we have converted the point in polar coordinates given by 2 pi over 3 to Cartesian coordinates 1 square root of 3. And so this pair of formulas uniquely gives the expressions for x and y in terms of r and theta. So whenever we want to convert a point in polar coordinates to Cartesian coordinates, we have to use these two formulas. Now, regarding the backward conversion, that will be a little bit more delicate. So let us look at the following example, number 4, which asks to do the converse of what we just did. So we will be given a point in Cartesian coordinates no, that's actually correct. I had minus 1, 1, 2 polar coordinates. So this silently assumes that this pair here is coordinates of our point in the Cartesian system. Okay, so again, we will need our picture over here. So what it tells us about the right rectangle here, so we want to consider the right rectangle like so, with sides x and y, length x and y, and angle theta. So this here is the angle theta. Now from this rectangle, let me remove the relevant parts. From this right triangle, I have that r, being the hypotenuse in this triangle, is equal to the square root of x squared plus y squared, and theta can be determined, for example, as inverse tangent of y divided by x, because x and y are the length of these sides in the right triangle, so I have to divide opposite side by the adjacent side. That gives me tangent of theta, and then I take inverse tangent. Now, there's a little detail here, so we have to be a bit careful because tangent takes the same values in the first and third quadrant, so it is positive in the first and third quadrant. So we must have a way to distinguish between points that live in these two quadrants, and similarly for the second and fourth quadrants. And so we may have to add pi depending on the quadrant. So for example, for our particular point, here's how we use this formula. So this formula will be used whenever we have to convert Cartesian coordinates to polar coordinates. We have to apply these formulas. And so the term of plus pi may or may not be there. It depends on the quadrant. So let's illustrate this formula now by converting our particular point minus 1, 1 to polar coordinates. So we have the point, let's see, actually it's easier if I just draw a new picture. So I have the coordinate system right here, and I have the point minus 1, 1. So this is the point with Cartesian coordinates minus 1, 1. And my goal is to convert it to polar coordinates. So first, I can easily compute r as the square root of x squared plus y squared. So that is square root of 1 squared plus, that would be minus 1. Minus 1 squared plus 1 squared, which gives me square root of 2. So the r, the value of the polar radius, is uniquely defined by this by this pair of Cartesian coordinates. Now, theta, on the other hand, is given by our formula here. So theta is the inverse tangent of y divided by x. So that is plus possibly pi. But now let's just go ahead and compute the inverse tangent. So it's inverse tangent of 1 over minus 1. Giving us inverse tangent of minus 1, which is, if you recall how inverse tangent works, it gives you values between minus pi over 2 and pi over 2, and in this case it's going to give you minus pi over 4, which corresponds to a point somewhere in the fourth quadrant. So minus pi over 4 gives you angle pointing in this direction. So it gives you a point somewhere here, as opposed to this point in the, instead of this point in the second quadrant. So since we are not happy with this point that corresponds to the angle minus pi over 4, we're going to add pi to it so we will indeed have to use the plus pi option to end up in the second quadrant as desired here. So now we conclude that this point here has polar coordinates square root of 2, 3 pi over 4. It's easier to check that indeed a point with such polar coordinates lives in the second quadrant. And so in this case, we have indeed to add pi in order to arrive at a point in the second quadrant. So since the values of arctangent are always either in the first or fourth quadrant, to get points with polar coordinates in the right quadrant, if it's in the left half plane, we always have to add pi to the angle. And so let us again write down the conversion formulas that we arrived at previously. So we have that given polar coordinates are theta, to convert them to x and y, you have to use this pair of formulas. And in the opposite direction, going from Cartesian coordinates to the polar coordinates, formulas are as follows. And theta is the inverse tangent of y over x plus possibly pi, depending on the quadrant. And so these are the conversion formulas to be used whenever you have to go between polar and Cartesian coordinates.